Hi everyone. Today let's talk about sessions 3.5, Matrices of Relations. We use matrices of relation to represent the relation R from X to Y. We first label the rows with elements of X. Then we label the columns with the elements of Y. We set the entry in row X and column Y to 1 if X are Y, and to 0 otherwise. So given the matrix, let's say we have 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. Okay, and then we say, let's make it more interesting. Okay, so we say these are the rows. So you can see here we have 3 rows. And these we call columns, and we have 4 columns. Okay, and so we say this is the size of the matrix is 3 by 4. So we say the row first, and then we say the column. Okay, so row by column. Okay, so let's look at the example. We want to find the matrix of relations R equals 1b, 1d, 2c, 3c, 3b, 4a. Let me matrix. Let me fix this. Okay, for x equals 1, 2, 3, 4 to y equals a, b, c, d. Okay, so we draw the matrix, and the x, we have 1, 2, 3, 4. So we label the elements of X as the rows, and then for the elements of Y, we label them in the columns. So A, B, C, D. And then let's look at our relation 1B. So we have first row 1, and then B. So this is 1. Okay, and then next one 1D. So 1 here, D right here, so 1D, 2C, so 2 here, C here, so 2C, 3C, so it's right here, and then 3B is here, 4A right here. So after we fill the ones corresponds to the relation, the other entries we just fill with 0. Okay, so we fill the 1 first when corresponds to the relation, and then the other entries we just fill with 0. So far so good, everybody? Yeah, very easy, right? Okay, let's continue. So in this case, if we have a relation on a set X, then what do? We just put the elements A, B, C, D in the row and columns. And then look at the relation. AA, so AA here. BA, so BA here. So here. CD, so CD here. And then DD is right here. CB is here. BC, so BC here. Okay, so after we finish filling in the 1, then the other entries just zeros. Do you get the same answer? Yes. So just keep in mind the X is on the rows, and then the Y is on the columns. But if we have a relation R on the X, so it's like a binary relations on the Cartesian product XX. So you put you label X in the rows and columns as well. Then you just look at the relations and fill in the ones. Okay, and then the other entries just fill with the 0. Okay, next, let's talk about matrix operations. So an M by N matrix, okay, A, with entries Aij. So let's denote this Aij, and where where I is the row number and J is the column number. So that's why we have A11, A12, dots, A1N, and then we have AM1, AM2, dots, AMN. So this matrix has M rows and columns. Okay, so how do we add two matrices? So first of all, they must be the same size. Okay, so same size means M and N must be the same. Okay, so two matrices A and B, they must be in the same size. So they have the same number of rows and same number of columns. And then when we add them, we'll just add the entries, the corresponding entries together. Okay? So let's look at example. What is the size of A? So we have 2 rows and 3 columns. So this is 2 by 3 matrix. How about the size of matrix B? We have also 2 rows and 3 columns. Matrix C, 2 rows and 2 columns. So part A, we want to find A plus B. So A plus B is, first of all, do they have the same size? Yes, they are both 2 by 3, so we can add them. So we add the entry, the corresponding entries together, right? So 0 minus 3 minus 1 plus 6, 2 plus 9 minus 7 plus 0, 5 minus 2. Okay? And then we continue to calculate. 3 plus 4, 7, this negative 3, 5, 11, minus 7, and 3. Okay, so this is A plus B. So far, so good, everybody? Part B, A plus C. Are they in the same size? No, so this is undefined because they're of different size. Okay, so we cannot add them. Next, multiply a matrix by a constant is simply just multiply each entries by the constant C. So continue with last example, find 3A. So A is there. 3A is 3 times the matrix 3, 2, 0, negative 7, negative 1, 5. Okay, so we have 3 times each entry. 3 times 3, 9. 3 times 0, 0. 3 times minus 1, minus 3. 3 times 2, 6. 3 times minus 7, minus 21. 3 times 5, 15. So far, so good, everybody. So we multiply each entry in the matrix by 3. Okay, next is the key parts. How about matrix multiplication? Okay, so how do they multiply together? Okay, so suppose we have matrix A, matrix B. So let's see the products. Then what's the dimension? Well, the dimension of A is M by N. Then the dimension of B must be M by P. Okay, so matrix multiplication, we need to make sure the inner dimension must match. So if we have A times B, then the inner dimension, you can see they're both N in this case. And then the output, the matrix multiplication, the result C is gonna have size M by P. So the outer dimension will give us the dimension of the result C. Okay, so you can see here we have this is M by N, this is M by P, and then our result is gonna be M by P matrix. And how to calculate? We use row times columns. So we use rows times columns. So for each I, J entry in C, we're gonna pick the ith, so the ith row of A, and then we multiply by the J column of B. Okay, so then we multiply the entry respectively. So I will explain how this works in an example. Okay, so probably the easier way to understand this as a series of matrix vectors multiplies. So we can consider the each columns of B as a vector. Then this guy is the matrix B, and then each Ci is now the matrix A times the vector B. Okay. All right. Let's see, how do we calculate? So, oh, I think I missed something here. I mean AC. Okay, so what is the matrix A? This is 2 by 3. What's the size of C? 2 by 2. Okay, let's look at AC. Well, AC is 2 by 3, and this is 3. This is 2 by 2. Does the inner dimension match? Uh-oh, don't match. Then we say this guy is undefined. Okay, next, CA. Well, C is 2 by 2, A is 2 by 3. You can see the inner dimension match. So this is defined. Okay, so let me copy it down here and show you how to calculate. Okay, so how do we calculate? First, we're gonna use the rows of C multiply the columns of A. Okay, let me change the color. Okay, so for the 1, 1 entry, we use the first row of A multiplied by the first column of, the first row of C multiplied by the first column of A. Okay, so you can see it's gonna be 3 times 3 plus minus 2 times 2. So 3 plus 3, 3 times 3 plus minus 2 times 2. Okay, and then let's continue. So that's the first row times the first column. And then the next entry, 1, 2 entry, we use the first row times the second column. So 3 times 0, and then plus minus 2 times minus 7. Oh, no more space. Okay, so far so good. And then we use the first row times the third column. Okay, so we have 3 times minus 1 plus minus 2 times 5. Okay, and then for the second row, we use the second row of C multiplied by the first row of the first column of A. Okay, then we have minus 1 times 3 plus 6 times 2. Okay, for the second entry, we use the second row of C multiplied by the second column of A. Minus 1 times 0 plus 6 times minus 7. Then last entry, we use the second row of C multiplied by the third row column of A. So minus 1 times minus 1 plus 6 times 5. Okay, what do we get? 3 times 3, 9. 9 minus 4. Next entry, 3 times 0, 0. Negative 2 times negative 7, 14. Then negative 3 minus 10. Then we have minus 3 plus 12. Then here 0 minus 42. Here 1 plus 30. Okay, so our result is 9 minus 4. Let me see, can I move this to the left a little bit? I ran out of space there. Okay. Alright. Okay. So my answer, 9 minus 4 is 5. 14 stay here. Negative 3 minus 10, negative 13. 12 minus 3, 9. Negative 42, 31. So this is the result. And you can see the result is actually 2 by 3. Okay, the result is a 2 by 3 matrix. So far so good, everybody. Alright, let's continue. Okay, so I hope everybody can stop the video here and try to work on this problem. Okay, after you're done, you can continue to play the video and check your answers. Are you done? Okay, let's start. Let me see. Let me change back to this color. So what's the size of A? How many rows? 3. How many columns? 2. Have a matrix B. How many rows? 2. How many columns? 4. Okay, so what is AB? Well, AB is 3 by 2 times 2 by 4. Does the inner dimension match? Yes. So, let's put down the matrix here. Okay. Minus 1, minus 2, 6, 4, 1, minus 3, minus 1, minus 1. Okay, so how do we calculate? We're gonna use the rows times the column. So rows times column. 1 times minus 1 is minus 1. Plus 2 times negative 2. Okay, next we use the first row. So this entry is in the first row, second column. So that's why we use the first row of A times the second column of B. So 1 times 6 is 6. 2 times 4, right? Next, use the first row of A multiplied by the third column of B. 1 times 1, 1. And then 2 times negative 3. Finally, 1 times minus 1, minus 1. 2 times minus 1, minus 2. Okay? And then next, we're gonna have a longer one. Okay, next is the second row of A times the first column of B. Negative 2 times negative 1, so it's 2. 1 times negative 2, negative 2. Okay. Next, negative 2 times 6. And 1 times 4 is 4. Next, negative 2 times 1 is negative 2. 1 times negative 3, minus 3. Last, negative 2 times negative 1 is 2. 1 times minus 1 is minus 1. So here we're using the second rows of A multiplied by the last column of B. Okay, finally, so last row of A times each column of B. So minus 3 times minus 1, 3, and then because it's 0, it's gone. And then minus 3 times 6, right? And then plus 0 times whatever is 0. Negative 3 times 1 is negative 3. Negative 3 times negative 1 is 3. And then because it's 0 times whatever is 0. Okay, what do we have? Minus 1, and then this is minus 4. 6 plus 8. 1 minus 6. Negative 1 minus 2 is negative 3. 2 minus 2 is 0. negative 12 plus 4, negative 5, 1, 3, minus 18, minus 3, 3. So in the exam, you have to show all your work, okay, if you have some questions like this. I know your calculator can help you to do matrix operation. And so I really hope that in your homework and your exam, please do it by hand, okay? Show all your work. And then after you are done, you can use your calculator to type the matrix in it, to input the matrix, and then do the matrix addition or multiplication, and then you can check your work. So you only use the calculator to check your work, okay? In this case, we can learn it. Okay, minus 12 plus 4 is minus 8, and then minus 5, 1, and then we just copy down those entries. Okay, so this is our result. So far, so good, everybody? Okay, how about BA? So BA, well, B is 2 by 4, A is 3 by 2. Does the inner dimension match? No, so this is undefined. You can see this is matrix operation is not commutative. Okay, this is the example of not commutative operator. Okay, so AB is not equal to BA for matrix multiply. Okay, and here we have some rules of matrix algebra. The addition is commutative because remember when we add to matrix, we just add the entries respectively, and then inside each entry is just addition of numbers. Addition of numbers is commutative. Okay. And then for addition, we also have associative law for addition. We can add the last two matrices together and then add the first one, or we can add the first two matrices together and then add the third one. And for the multiplication is actually associative. We can multiply BC first and then multiply the A in front, or we can multiply AB first and then multiply C on the right. But remember, matrix multiplication is not commutative. You cannot switch the order of ABC, okay? Alright. And we also have the distributive law. So A times B plus C equals AB plus AC. A plus B, parentheses, times C is AC plus BC. Okay? Alright, let's come back to our relation. Okay, so if remember our matrix of relations are from x to y, we put x is the elements of x correspond to the rows, and then the elements of y we labeled on the columns. So when we see a relation, we fill it with 1, and the rest is just gonna be 0. Okay, so questions. If R is reflexive, what does the matrix look like? Okay, what is special about reflexive? Well, reflexive example, if X is, let's say, A, B, C, reflexive means R must contain, okay, R must contain A, B, and C, right? And then if we want to draw those pictures, let's say ABC here, ABC here. By the way, the order of the elements might change. You can fix the order ABC, or you can use the order BAC or CBA. Doesn't matter. Okay. So AA, so you have this, AA, BB is here, CC is there. So other entries, we don't know, maybe 0, or if we have a relation there, then it's 1. Okay, but we're sure that the diagonal entries must be 1. Okay, so what does the matrix look like? The diagonal entries must be 1. Okay, to be reflexive, we have the diagonal elements must be 1. Next, if R is symmetric, what does the matrix look like? Okay, let's see. So similarly, let's say X is ABC, and then let's say if AB is in R, then what happened? Because R is symmetric, then BA must be in R. Okay, what does that mean? Let me draw it here. So ABC, ABC. So if AB is in R, then BA, where's BA? Right here. So you can see, this is 1 and this is 1. So, and all the other entries we don't know. Okay. So, and you can say here, this matrix is symmetric. Okay. So, what's special about the matrix? The matrix is also symmetric. What does that mean by saying a matrix is symmetric? If a matrix is symmetric, then we can see it's a mirror image about the diagonal. Okay, so which means whatever number here, when you flip it over, so you see this diagonal is like the mirror. When you flip it over, you get the same thing here. Okay, so we say matrix, in that matrix, we can see mirror image about the diagonal. Okay, so i.e. aij equals aji. Okay, so this is the ith row, and jth column. Okay, it also equals the jth row and the ith column. Okay, so let me give you an example of a symmetric matrix. So if we have 1, 2, 0, 3, minus 4, something like that, and let's say this is 5, something like this. Okay, because it's symmetric, then let's say this is diagonal, right? So 2, so this must be 2. This is 0, this must be 0. This is minus 4, this must be minus 4. So you can see it's a mirror image about the diagonal. Okay, so this is the symmetric matrix. And you can also see for a relation. So we can see for relation matrix, the entries are either 0 or 1. Okay, it is a kind of an easier entry. Okay, so if that relations, the entry corresponds to the relations, isn't it? Then we fill with 1. If they are not related, then we fill with 0. Okay, next. If the relation is transitive, what does the matrix look like? So here we have a theorem. Let R1 be a relation from X to Y, and let R2 be a relation from Y to Z. Truth ordering of X, Y, and Z. Let A1 be the matrix of R1, and let A2 be the matrix of R2 with respect to the ordering selected. Then the matrix of the relation R2 composite R1 is obtained by replacing each non-zero term in the matrix products A1, A2 by 1. Okay, so you can see composition of the relation actually corresponds to the matrix products. Okay, but matrix products will create the entries of the matrix products might not be only 0 and 1, it could be other numbers, right? But what do is we replace the non-zero number by 1, then that matrix is the relation matrix of the composite relations R1 composite R2 composite R1. Let me maybe put it down here. Okay, so we have the relation R2 composite. Okay, so R2 composite R1. Okay, and we have the matrix products A1, A2. So and then so first you calculate the matrix A1, A2, and second you replace the non-zero entries by 1, and then you get the new matrix. Okay, so this is new matrix is the relation matrix of R2 composite R1. Okay, a remark is you see the order. This is A1, A2. So A1 go first times A2, and then before the relation matrix is R2 composite R1, because R2 composite R1 is you do R1 first and then you do R2, right? And then the composite is R2 composite R1. Okay, so all right, so let's consider the relation AA, BB, CC, DD, BC, and CB. If we write down the relation matrix, you see AA, BB, CC, DD. So we have this guy, this guy, this guy, and this guy, the diagonal elements. And then we have BC. So BC is right here, CB is right here. So that's why we get this relation matrix. Okay. Next, I want you to look at A times A. So here, what's the size of A? Is 4 by 4. So we also say this is a square matrix. If the number of rows equals the number of columns, we say this is a square matrix. Okay? So, and then we can define A square. So, oh, sorry, I pressed something wrong. Okay, so what is A times A? Okay, so let's see. A times A is, let's copy them down again. So 1 0 0 0 0 0 0 1 1 0 1 1 0 0 0. Oh, actually, can you see this matrix is symmetric? You see, this is the diagonal, and then we can see it formed a mirror image about the diagonal. So this matrix is symmetric. Then, so we can tell now the relation R is a symmetric relation. Okay, let's continue. Put down my A. Okay. Now, let's compute the products. So we use first row times the first column. So 1 times 1 is 1. And then the zeros follows just zeros. Next, we want to use the first row times the second column. Well, you see, 1 times 0, and then you plus 0 times 1, and then the zeros. So that's why you only get 1, okay? Then continue 1 times, ooh, you see 1 times 0. So this is also, oh, sorry, I said it wrong. This is 0. And the last entry, 1 times 0 plus 0 times 1, this is also 0. And the last entry, 1 times 0 is 0, and all the rest is 0. Okay, so we get the first row of their products. Okay. Next, second row times the first column, 0 times 1, 0, 1 times, so let me put it down here, 0 times 1, 1 times 0, and all the rest is 0, so we get this is 0. And then the second row times second column, so 0 times 0, and then we have 1 times 1 plus 1 times 1, Ooh, so we get 2 right here. Second row times third column, same thing. We have 0 times 0 plus 1 times 1 plus 1 times 1 plus 0 times 0. So we also get 2. The last row we have 0 times 0, 1 times 0, 1 times 0, 0 times 1. So the result is 0. Okay, one more. So do you see the second row and the third row are the same? So your results, your second row and the third row is gonna be the same. That saves us some time. Okay. Last row, 0 times whatever 0. The last entry is 1, but 1 times the 0 is 0. Next, last row of A times the second column. So 1 times 0, we give 0. 1 times 0, get another 0. Ooh, look at the last entry. So all those 0 times 0 is 0. And then we have 1 times 1 is 1. So that's why our result is 1, 0, 0, 0. And we have 0, 2, 2, 0, 0, 2, 2, 0, 0, 0, 0, 1. Okay, so and this is the result I give you. You can see they are the same. So far so good, everybody. All right. Now we place all the non-zero entries of A squared by 1. We get a relation matrix B for R composites with R. Then this is the relation B. Okay, now I want you to compare this matrix B and our original matrix A. See, this guy and this guy. What happened? They are the same. So if actually this is the fact, if they're the same, then the relation R is transitive. Okay, so again, how do we get it? So first, you want to compute the matrix A squared. Okay, that's the first step. And second, you're gonna get the relation matrix for R composite R. And how do you do it? You just replace the non-zero entries of the products by 1. Okay? And then the third step, you compare with the matrix A. If they're the same, then you can conclude R is transitive. Is that clear, everybody? Let's do one more example. Okay, so consider R is this relation, AA, that give us this guy, BB, CC, DD, AC right here, CB right here. So that's why this is our, this is our relation matrix. Okay, so far so good, everybody. Okay, let's continue. So let's compute A squared. Okay, so A squared, this is a 4x4 matrix, so matrix multiplication is defined. So A squared is 1 0 1 0 0 1 0 0 0 1 1 0 0 0 0 1. Okay, multiply by the same thing. Okay, let's continue. Let me use a different color. Which color do you like? How about purple? So we use the first row times the first column. So we have the 1 entry. So 1 times 1 and then plus 0. A lot of zeros. So it's just gonna be 1. Oops. Okay. So it's just gonna be 1 times 1, which is 1. Okay. And then first row times second column. 1 times 0 is 0. 0 times 1 is 0. Okay, let me put it down here. So 1 times 0 plus 0 times 1. And then we have 1 times 1, and then we have 0 times 0. Okay, so if you like, you can put down all those details. Okay, next, first row times the third row, and then we have 1 times 1 plus 0 times 0 plus 1 times 1 plus 0 times 0. Okay, and oh, I forgot to say, what is this guy? This is 0, this is 0, this is 1. Okay, so our result is 1. This is 1 plus 1, so 2. Eventually, we have, oh, those are a lot of zeros. So the only non-zero is the last entry, but this guy is 0. So we just get, oh, I erased more than that. Okay, so that's why we get 0 in this entry. Okay, let's look at the second row. Second row times the first column. 1 times 0, and then 0 times whatever is 0. So it's going to be 0. And then this guy times the second column. 0 times 0. 1 times 1 plus 0 times 1 plus 0 times 0. So this gives us 1. Next, 0 times 1, 1 times 0, 0 times 1, 0 times 0. So that gives us 0. Last entry, because the 1 is only the non-zero ones, so but this guy is 0, so we also have 0. Okay, and then the third row times each columns. 1 times 0 is 0, and then 0 times 0, 1 times 1, 1 times 1, 0 times 0. This gives us 2. And then 0 times 1, 1 times 0, 1 times 1, 0 times 0. So this gives us 1. And then last one, because this guy is 0, 0 times 1 is 0. Okay, almost there. Last row. So the only non-zero entry is the 1. 1 times 0 is 0. 1 times 0 is 0, 1 times 0 is 0, 1 times 1 is 1. So we have, this is 0, this is 0, this is 1. Okay, so our result, 1, 1, 2, 0. Second row, 0, 1, 0, 0. Third row, 0, 2, 1, 0. Last row, 0, 0, 0, 1. So this is what we get. So far, so good, everybody. Alright, let's replace all the non-zero entries by 1. So these are the non-zero entry. We replace the entries by 1. Then we get the relation matrix. This is a relation matrix. Okay, now compare this guy with our original matrix A. Are they the same? Oh, do you realize? This is what I highlighted here. Do you see this entry? It was 0, but now it's 1. All the rest, other entries are the same, but except this one. So, but because of one entry is different, then we know those two matrices, they are different. So we can say R is not transitive. Okay. So far, so good, everybody. Okay, let's summarize. How do we tell relation is reflexive? Well, we look at the relation matrix. If the diagonal elements are all 1, then we know the relation is reflexive. How about symmetry? Okay, if the matrix of relation is symmetric, then we know the relation is also symmetric. But for transitive, well, it requires more work. First, you want to compute the relation matrix A, you want to compute A squared. So that's the matrix multiplication. And second step, when you see the non-zero entries, we place it by 1 to get the relation matrix for R composite R. And then you compare this relation matrix B with the original matrix A. If they are equal, then the relation R is transitive. If they are not equal, then the relation R is not transitive. So far, so good? Yeah, so reflexive, symmetric, and transitive are very important properties because you remember relation is an equivalence relation if it is reflexive, symmetric, and transitive. And a relation is a partial order if it is reflexive, anti-symmetric, and transitive. Okay, so that's it about chapter 3. Please go ahead and work on your homework. If you have questions, feel free to print screen and send me your questions or ask me in class or office hours. Have a nice day. Bye.